Good morning. Today we are going to discuss lossless and dependency preserving decomposition. A decomposition of a relation is done when a relation in relational model is not an appropriate normal form. Relation R is composed of into two or more relations if decomposition is lossless, join as well as dependency preserving. So when you are decomposing a relation into two or more relations, then that decomposition should be lossless as well as dependency preserving. How will you check whether a decomposition is lossless? There is a technique, and I will explain that with the help of one or more examples. The condition is if you decompose a relation into R1 and R2, then decomposition is lossy if R1 natural join R2 is a subset of R. That means some data has been lost. If the decomposition is lossless, then the natural join of R1 and R2 should give R. To check for lossless join decomposition using functional dependency set, following condition must hold. Union of attributes of R1 and R2 must be equal to the attribute of R. That means if a relationship has say 6 attributes, and suppose that you have split into 3 tables or 4 tables, then if you take the union of all those attributes, then that should be the same as that of R. That is attribute of R1 union attribute of R2 is equal to attribute of R. Then intersection of attributes of R1 and R2 must not be null. That means there should be some attributes which is taking part in both R1 and R2. Otherwise, you can't have a natural join operation. Common attribute must be a key for at least one relation. These are the conditions that you have to have. If you are splitting a table into two, then the attributes of R1 union R2 should be equal to attribute of R. Then attribute of R1 intersection R2 not equal to 5, and the common attribute should be a primary key for either of two tables. That is, and there is an algorithm for checking whether a decomposition is lossy or not. That we will discuss in the later part of this lecture. And now, next is how do you check whether a decomposition is dependency preserving. If we decompose a relation into say R1, R2 and R3, then all dependencies of R either must be part of R1, R2 or R3. That means if you have a number of dependencies and if you are splitting that into different tables, then those relationships should be preserved. That means that should exist in either of the tables, or that or we should be able to derive from that these set of tables. Okay, must be derivable from the combination of functional dependencies of R1 and R2. Okay. For example, a relation ABCD with functional dependency A derives BC is decomposed into R1 of ABC and R2 AD, which is dependency preserving because F derives BC is a part of ABC relationship 1. Okay. And we are going to check whether that decomposition is lossless or not. That means when you are decomposing a table into, or when you are splitting a table, then the resultant table is not lossless or not. If it is lossless, you can go for that, and if it is lossy, then you cannot do that. Okay, for that, there is a testing algorithm, and the algorithm is like this. Here I am having a relationship which is having SSN, E name, P number, P name, P location and hours, and I am going to split this table into two. R is, you are going to split this R into R1 and R2. Okay, R1 is having E name and P location, R2 is having SSN, P number, P name, P location, hours. For that, you are going to construct, or you are going to have a table like this. You are going to have a table, and this table is having how many rows? This is a table, and we are going to have all the attributes here: SSN, ename, p number, p name, p location, and finally hours. Okay. Now you are going to split that into two, that is R1 and R2. Then for each of these tables you should have a row. Actually, so for each row you are going to have a row. That is, this one represents R1 and this represents R2. Okay. Now I am going to have, say, type B11, B12, B13, B14, B15, B16, B21, B22, B23, B24, B25, and B26. Okay, that means you have to construct a table and it should have how many rows? If you are splitting this into three tables, you should have 3 rows. If you are splitting this into 4 tables, you should have 4 fours, like that. Here I am going to split this into 2. That's why we have only 2 rows, R1 and R2. Now I am going to rename this as this is row number 1, B11, B12, B13, etc. up to B16. This is B21, B22, etc. up to B26. Then I am going to have, this is A1, this is A2, A3, this is A4, A5 and A6. So these are the columns. Now here R1 is having ename and p location. Ename and p location. R1 is having ename. So there I am going to replace this with A2. This is going to have A2. Then ename and p location. This is p location. Now this is having A5. This is A5. Now for R2, SSN, P number, P name, P location and hours. So for R2, SSN is having, say, A1. I have replaced this with A1. Then SSN, P number is this one. Here I have to replace that by A3. Then P name is this one. So I have replaced that with A4. P location is A5 and hours is A6. Okay. Now, so this is the initial table. That means before starting the algorithm, this is the content of our table. That means initially what you have to do is you have to construct a table. It should have how many rows. After decomposition, how many tables should be there? That one represents the rows, and columns means in the original table how many attributes are there, that much attributes, and that should be numbered like this, A1 up to A6. 6 different attributes are there, 1, 2, 3, 4, 5, 6. Then after that, in R1 row, the attributes are ename and p location. That is why we have A2 and here we have A5. For R2, how many? 1, 2, 3, 4, 5. 5 attributes are there. That means here SSN, P number, P name, P location, house. Okay. Now here, this is the initial start before starting the algorithm. Then take each functional dependency. Here functional dependency number 1 is SSN and ename. SSN. So this is the row, this is the column corresponding to SSN, and you have to go through that column and you have to check whether the entries, whether two entries are same. Here it is B11 and here it is A1, so there is no possibility for any corrections or something like that. Okay, that means left hand side is SSN, and that one you have to, that row you have, that column you have to select, and you have to check for same entries. Here this B11 and A1, those entries are different. Now next is, that means we have evaluated this one. Now we are going to P number determines P name or P location. P number determines P name. Left hand side is P number. P number means this column. In that column also B13 and A3 are different. So this one also over. Now SSN P number determines ours. SSN and P number. SSN and P number. So here it is Y11, B13, A1, A3. So all those are different. So here there is no possibility for any rewriting or something like that. So here we don't have. So after this processing, no change has been occurred for this table. And here see, you have to look for any row which is having all A's. You have to look for. Here this is having B, this also is having B. That means if there is a row which is having all A's, all the rows are filled with, all the entries in a particular row is filled with A's, then that is lossless. This is a lossy decomposition. This is lossy. Now we are discussing another example which is the same R. Now I am going to split that into three, R1, R2 and R3. Here for that I have constructed a table, same 6 attributes, and those attributes are defined as A1, A2, A3, A4, A5, A6. Now this is R1, R2 and R3. So I am going to have B11, B12, B13, B14, B15, B16. This is B21, B22, B23, B24, B25, B26. This is B31, B32, B33, B34, B35 and B36. So after that, the tables we are going to construct, R1 is SSN and E name. R1 is this row represents R1, and in that SSN and E name. So SSN is, you are going to replace this by A1, and E name also you are going to replace that by A2, A1 and A2. Then P number, P location, P name for R2. R2 is having P number, P location, P name. P number, P location, P name. Now here I am going to have A3. This is A4 and this is A5. Okay, that means P number, P location, P name for this is relationship R2. Relationship R2, A3, A4, A5. Now R3 is having SSN, P number and hours. SSN, P number and hours means SSN is A1. P number hours. What is P number? P number we are going to have A3, and hours you have A6. So the initial setup is over. Now we are going to take this functional dependencies one by one. That is SSN determines E name. SSN determines E name. Left hand side is SSN, and we are checking for two columns or two entries with the same SSN. That means A1, B21, A1. Here this A1 and this A1 are same. Then we are going to check the value of E name. Here it is A1 and here it is A1. That means this is an exact replica. And SSN determines E name. E name, here it is A2, here it is B32. Now I am going to replace this by A2. Okay. That means here it is same, here it is different. So SSN determines E name, then definitely I have replaced this by A2. Okay. Now P number determines P name. P number column. Here it is A3, here it is A3. And what about P name? P number determines P name. P name, here these two are different. A4 and B34. Now I am going to make this as A4. That is about P number determines P name. P number determines P location. P number, here two entries are same. What about P location? Here these two are different. So I am going to replace this by A5. A5 and now SSN P number determines ours. SSN and P number collectively. SSN and P number. Here these two are different. These two different and these two different. Okay. So there is no possibility for further replacement or further rewriting. Now you have to look for rows which is having A's only. Here we have A's, but here there is a B. Here starting from B, here A1, A2, A3, A4, A5 and A6. That means here we have a row which has all A's. So this is a lossless decomposition. If there is a row which is having all A's, then that is a lossless decomposition. This is the way you can check whether a decomposition is lossless or not.